Hello everyone. Have you ever looked at sunlight through a glass of water and noticed tiny rainbow streaks? That's because white light is not just one color, it's a whole family of colors hidden together. The prominent members of this family are violet, indigo, blue, green, yellow, orange, and red, in short, VIBGYOR. Each color is unique because it has its own wavelength. And here's something fascinating. The wavelength is the true fingerprint of a color. No matter where the light comes from, a bulb, the sun, or even a laser pointer, if it looks violet, it will always have the same wavelength. That's why physicists say color is the characteristic of wavelength. Now, let's connect this to physics. Why does light bend differently for different colors inside glass? The answer lies in something we call refractive index. The refractive index of glass, written as glass, is simply the speed of light in air divided by the speed of light in glass. Nu of glass is equal to the speed of light in air divided by the speed of light in glass. Here's the key. In glass, violet light moves the slowest, while red light sips through fastest. And since a lower speed means a higher refractive index, we get violet greater than red. So, in the race of colors inside glass, violet drags its feet and red sprints ahead. Alright, let's take it a step further. Remember Snell's law from earlier? It says mu equals sine of I divided by sine of R. Here I is the angle of incidence and R is the angle of refraction. If we rearrange, we get R equals sine inverse of sine I divided by mu. Now watch the logic unfold. When mu is bigger, R becomes smaller. That means violet, which has the largest mu, bends more sharply, giving a smaller refraction angle. Red, with the smallest mu, bends the least, giving a larger refraction angle. So, inside the prism, violet dives in steeply while red takes a wider path. Once the light emerges, the bending is visible as deviation, represented by the formula delta equals I plus E minus A, where I is the angle of incidence, E is the angle of emergence, and A is the prism angle. Since violet has a smaller refraction angle inside, its deviation violet turns out to be larger. Red, with a bigger refraction angle, ends up with a smaller deviation red. Therefore, the inequality is clear: violet is greater than red. In simple words, violet bends the most, red bends the least. And that's why when white light passes through a prism, the violet beam appears at the bottom and the red beam at the top. Let's test this with some numbers. Suppose a prism has angle A equal to 60 degrees and the ray enters at an incidence angle I equal to 50 degrees. For violet light, the refractive index mu is 1.53 and for red light, mu is 1.51. Step 1. Apply Snell's law. For violet, R equals sine inverse of sine 50 divided by 1.53. For red, R equals sine inverse of sine 50 divided by 1.51. Step 2. Use the prism condition R1 plus R2 equals A to find the second refraction angle. Step 3. Calculate the angle of emergence E for each color. Step 4. Substitute into delta is equal to I plus E minus A. When you compare the two, you'll see that the deviation of violet is indeed greater than that of red. This numerical check confirms what theory already told us: smaller wavelength means larger deviation. Let's bring it all together. White light is a mixture of 7 colors, each defined by its wavelength. In air, they all move at the same speed. But in glass, violet slows down the most, red speeds up the most. Thus, the angle of refraction for violet light is less than the angle of refraction for red light, and the angle of deviation for violet light is greater than the angle of deviation for red light. That's why dispersion occurs. A prism separates white light into a spectrum from violet to red. So next time you see a rainbow in the sky or sunlight dancing through a prism, remember, it's physics painting the canvas with wavelengths deciding the colors. Isn't that beautiful? See you in the next session.